Welcome to Demystifying Math. In this lesson, we're going to be looking at the derivatives of logarithmic equations. The first derivative of the log of x is 1 over x. When you have an example like the log of 3x squared minus 2x plus 1, the 3x squared minus 2x plus 1 is going to go in your denominator. Then using the chain rule, we're going to multiply by the derivative of that trinomial, which is 6x minus 2. So our first derivative is 6x minus 2 over 3x squared minus 2x plus 1. For our second example, we have the natural log of x squared times 2x minus 1. In order to take the derivative, we're going to expand our log. So when you have a product, you're going to rewrite it as the sum of two separate logs. I also used the power property on the first product by bringing the 2 in front. So we have 2 log x plus the log of 2x minus 1. Now we're going to take the derivatives of the logs separately. So the derivative of the log of x is 1 over x, and we have a constant multiplier of 2. So for the first term, we got 2 over x. For the second term, you have 1 over 2x minus 1 times the derivative of the inner function, which is 2. So we have 2 over 2x minus 1. Now we're going to put this back together by finding a common denominator. So we're multiplying the first term by 2x minus 1 and the second one by x. Then we distributed the 2, so we get 4x minus 2, and added it to the 2x in the second fraction. Then combining like terms, we have 6x minus 2 for our numerator and x times 2x minus 1 for our denominator. For this problem, we have the log of the cube root of 2x minus 1 over x squared minus 3. We're going to approach this problem in the same way we did the last one, by expanding the logs. So the exponent would be 1/3, so we're going to bring that in front of the log, and then expand the log by subtracting those two, because this time we have a quotient. So we're going to take the derivative of 1/3 log of 2x minus 1. Well, we would have 1 over 2x minus 1 times the derivative of the inner function, which is 2, times the constant multiplier of 1/3. And for the second term, we did the same thing. The derivative of the inner function is 2x. Our denominator, taking the derivative of the log, will be x squared minus 3, and multiplying it by the constant multiplier of 3. Now we're going to pull them back together by finding a common denominator. So I'm multiplying the first fraction by x squared minus 3, and the second one by 2x minus 1. Then I'm going to distribute the 2x squared minus 6, and distribute the negative 2x, which gives me negative 4x squared plus 2x. Then combining like terms, I get negative 2x squared plus 2x minus 6 in the numerator. You can also rewrite that by putting the negative out front and changing the signs of all the numerators. For our fourth example, we want to find any extreme values of the natural log of e to the x squared plus 4. So we're going to start by taking our first derivative. So the derivative of the inner function is 2x times e to the x squared, and divide that by the e to x squared plus 4. Then to find the extreme values, we're setting it equal to 0. So the numerator can equal 0 when x is 0. In this case, the denominator cannot equal 0, so the only critical point we have is at 0. So we're going to test points on each side of 0. So I put in a negative 1, and I got negative 0.809. And then I plugged in a positive 1, and I got positive 0.809. This tells me that the graph is decreasing on the left side of 0 and increasing on the right side of 0, which means we have a minimum point at 0. So I plugged 0 back into the f of x function, and I got out log 5. So 0 log 5 is my minimum point. So that gives us a graph that looks like this. Decreasing on the left side of 0, increasing on the right side of 0, and an absolute minimum point at 0. For our fifth example, we want to find the direction and concavity of the graph. We have the natural log of the square root of 1 minus x over 1 plus x. The domain of this function is negative 1 to 1, exclusively. If you put in a negative 1, you would have 0 in the denominator. If you put in a positive 1, you would have a 0 in the numerator, and you can't take the log of a 0. So you can't include the endpoints. We're going to expand out the log first. So the square root is the same as a power of 1/2, so we brought the 1/2 in front. And then I expanded the logs by subtracting the ratios. And I'm going to take the derivative of each one of those. So for 1 minus x, the derivative is negative 1, and we're dividing by 1 minus x, and multiplying by a constant multiplier of 1/2. For the second one, the derivative of 1 plus x is 1, so we have 1 over 1 plus x times our constant multiplier of 1/2. Then we're finding a common denominator, so I multiplied the negative 1 by 1 plus x, and I multiplied the positive, the 1 in the second term, by 1 minus x. Then we're subtracting the two fractions, so I have negative 1 minus 1, which is negative 2, and negative x minus negative x, which gives us 0. So we just left with negative 2 in the numerator, which cancels with the 2 in the denominator. And I also changed the sign. So you see we had a negative 2 in the numerator and a 1 minus x in the denominator, which I switched the signs on that and got x minus 1. So that leaves me with 1 over x squared minus 1. The only critical points on that first derivative are where x is 1 or a negative 1. And since 1 and negative 1 are not part of the domain, we won't include it. So we don't have any critical values within its domain. So that tells us all we need to do to decide the direction of the graph is to plug in 1 point. So I chose 0, and I got out negative 1. This tells me that the graph is decreasing over its domain. Alright, so here's a picture of the graph, and you can see that it is decreasing everywhere on its domain. And I rewrote the first derivative as x squared minus 1 to the negative 1. And I'm going to take the second derivative to look at the concavity of the graph. So bringing the negative 1 in front of x squared minus 1 and reducing my exponent by 1, I got negative x squared minus 1 to the negative 2. And then we'll multiply by the derivative of the inner function using the chain rule, so the 2x. And then I just rewrote it as negative 2x over x squared minus 1 squared. So the only critical value on its domain is at 0. So we're going to test a point to the left side of 0, and I plugged in negative 1/2. And I got out 16 over 9, which tells me that the graph is concave up from negative 1 to 0. And then I tested a point on the positive side of 0, and I got out negative 16/9, which tells me the graph is concave down from 0 to 1. And that means that we have an inflection point at 0, 0. Okay, thank you for tuning in to Demystifying Math.